Alright, so this is my first attempt to do an online lesson. And chapter 15 is pretty short, and there's not a lot of information in that chapter that we need to know. The chapter is on waves. It's an introduction to waves and also an introduction to sound. So if we think about a wave, the first thing we probably think about is an ocean wave, since we live near the ocean. But a wave is a phenomenon. It's a disturbance that propagates either through a medium, which is just the stuff that the energy transfers through. In the example of a water wave, the water would be the medium. And if you've ever been hit by a wave, you know that a wave transfers energy. Now, all waves can be classified into two different categories. One is called a mechanical wave, and within a mechanical waves, the big difference between mechanical and electromagnetic is that with any mechanical wave, a medium is required. And an example of that would be sound. Electromagnetic waves, as the name kind of implies, has electrical components and magnetic components that we'll talk about later on in a different chapter. Certainly electromagnetic waves can pass through a medium, but their medium is not required. And an example of that would be light. Now, within mechanical waves can be broken down into two different categories based on how the wave moves in relation to the medium. And those two types of mechanical waves are called transverse and longitudinal. And with transverse waves, the wave moves, say, left to right, for an example, and the medium would move up and down. And that means that the medium is perpendicular to the motion of the wave. Longitudinal waves, if the wave is moving from left to right, the medium is also moving left to right. And I will give you an example of each of these. So here I have a computer simulation model that will show you a transverse wave. And as I start it, you can see the wave is actually traveling from left to right, but the generator is moving up and down. So if you look at the medium, it's moving up and down while the wave itself moves from left to right. Now, this is a simulation of a longitudinal wave produced by a speaker, and the speaker just moves back and forth, and it creates these compressions where the air is more compressed than usual. And you can think of those as the dark lines, and these lighter areas are regions where the density of the air is less than usual. And you can see that the waves, if you just look at this middle line here, the wave is traveling left to right, and the speaker that's producing it is moving back and forth from left to right. So the motion of the medium is parallel to the motion of the wave itself. Now, if I were to take a string and shake it up and down, it would generate a sine wave similar to the one that we're looking at here. And I want to talk about some characteristics of all waves, and I'm going to use this transverse wave as an example. So every wave has a frequency, and if you think about, well, let me back up and label some of these points. These points are called crests, and you probably already know this. And so let me type this in. And these lower points are called troughs, and you probably already know that. And we've already talked about amplitude, but let me just point out that the amplitude is the distance from the equilibrium position, which I have with this dotted line, to either a crest or a trough. So that represents the amplitude. Okay, so the frequency in terms of a wave definition would be the number of crests that pass a point in 1 second. And again, the unit for frequency is the same as it was before we talked about, which would be hertz. And if a wave has a frequency, that also means it has a period, and that is the time for one complete wave to pass a point. Another characteristic of any wave is the wavelength, and as the name implies, it is the length of a wave. And the easiest way to think of the length of one wave is the distance between one crest to another. And the symbol we use for the wavelength is called lambda, and it kind of looks like that. So you could say the distance from crest to crest is a wavelength, or the distance from trough to trough is a wavelength. Now every wave also has a wave speed or a wave velocity, and if we think about the speed of a wave, it's just the distance that a wave travels over some time interval. And what a way to think about that is the time it takes for one wavelength to pass a given spot. So one equation that we can use for velocity is the wavelength divided by the period. So that's one equation we can use. Another equation that we'll probably use more often is because frequency is 1 over the period and we're dividing the wavelength by the period, another equation we can use, and we'll probably use more than the first one, is the frequency times the wavelength. So these two equations can be used to find the wave velocity. Now these equations are a little misleading, because if you look at the equation mathematically, it would appear that the wave velocity depends on the frequency and the wavelength, but in fact the wave velocity doesn't depend on either of those things, and this is something you really need to remember. The wave velocity does not rely on the frequency or the wavelength. It only relies on the properties of the medium. So let's put that in here. And I'll try and demonstrate that with this little simulation. So we have this simulator again, and it's not running smoothly. Not sure why. But if we follow one crest across the screen, and kind of get an idea how long it takes, and this isn't showing up well because it's not running right, but I can change the frequency, and if I change the frequency, you can see that the wavelength, and I increase the frequency, you can see the wavelength has decreased. And if this was running correctly and we followed one crest across the screen, we would see that the speed of the wave is the same. So one thing you need to remember is that the speed of a wave depends on the properties of the medium. Now with this simulation, I can change the tension, which changes the property of the medium, and we'll see the well, that didn't work very good. Let's make the tension a little bit bigger, but different than before. And let me change this. So the tension's not as great, so the wave's not going to travel as fast. I know it's kind of hard to see, but by changing the tension, you're changing the properties of the medium, and therefore changing the speed. So what you need to remember here is that the wave speed does not depend on the frequency, it does not depend on the wavelength, it only depends on the properties of the medium. Another property that that's worth remembering is that because the velocity does not rely on frequency or wavelength, because the product of these two is a constant, the two quantities are indirectly related. So if the frequency doubles, the wavelength will go down by a factor of 2. So this is an example of a sound wave, and this is a speaker over here that I've tried to draw. And when the speaker moves back and forth, it creates regions of air that are more compressed, and those represent, on the diagram, those are represented by these black lines. So these are called compressions. And the regions in between the compressions, where the air is less dense than it normally is, and in the compressions the air is more dense, these are called rarefactions. And so you have a series of compressions and rarefactions, they alternate. To define the wavelength, I have that up here. The wavelength is, let me scroll that down. So the wavelength would be the distance from one compression to another. Or you could say from one rarefaction, the middle of a rarefaction, to the next. So longitudinal waves, sound being an example, they have wavelengths, they have frequencies, which it would be the number of compressions that pass a point per second, and they also have wave speeds given by the same equation. Now, a sound wave is also called a pressure wave because of the differences in pressure created by the compressions and rarefactions. And so something you should know is that, and in the compression region, it's a region of high density which corresponds to high pressure, whereas in the rarefactions there's a region of lower density and lower pressure than usual. And if you looked at a graph of pressure as a function of time, it would vary sinusoidally as well. Okay, the last topic in this chapter that we need to worry about is something called the Doppler effect, which you've probably heard from the Weather Channel or the weather stations using Doppler radar. But before we talk about that, let's just define what that means. And the Doppler effect is a shift in frequency because of the motion of the source and or the listener. And keep in mind that this effect refers to any kind of wave, not just sound or radar. There's many different examples you may have experienced. If you've ever gotten a speeding ticket because of a radar gun, the radar gun works basically off the Doppler effect. It can calculate your speed based on the frequency it sends out and the one that reflects off of your car. The sound that NASCAR, race cars make when they go past the TV, they start off at a high pitch and then they drop to a lower pitch. Sirens do the same way, or the same thing. And there's something called the redshift, which you may or may not be familiar with, but the redshift refers to light shifting to a longer wavelength, and this is evidence that our universe is still expanding. And I have a picture here. There are equations that go with the Doppler effect, but we don't need to worry about them. You just need to know when you'll hear higher frequency than usual or a lower frequency. And this little picture shows a siren coming towards one person and away from another. And basically what happens is that the wave fronts get compressed in front of the source, and that creates a smaller wavelength. And since the speed of the wave is the same, a smaller wavelength corresponds to a higher frequency. So if the source is coming towards you or you're coming towards the source, you will hear a higher frequency. And if it's moving away from you or you're moving away from it, you'll hear a lower frequency. So that's really all you need to know about the Doppler effect. Okay, I think I have 1 minute left. So this covers everything in chapter 15 that we need to know. The problems are really simple, just using that wave speed equation and frequency and wavelength. So if you have any questions, just see me during class, but hopefully you'll be able to understand everything I've presented here in this 15 minutes. Wasn't that fun?